Hello, welcome to our group presentation for ECEN 160's Lab 4. My name is Addison Steinagel, and I am joined by Chris Carrick and Michael Schmidt. Chris and I are both from Payson, Utah, and Michael is from Walla Walla, Washington. We are all software engineering majors. Today we will be discussing the ALU, its subcircuits, and how the principles of encapsulation are used to create functional subcircuits that help simplify digital design and enhance reuse of digital circuit layouts. Now, the bitwise AND circuit takes two 4-bit numbers, or nibbles, and then ANDs them together. It does this with each individual bit from the nibbles by taking one bit from each number and then ANDing them together using an AND gate. The result is then fed to the output. In a real-world application, this may be used to remove bits from a word that you are not interested in reading. Now, the bitwise OR circuit takes two nibbles and then ORs them together. It does this with each individual bit from the nibbles by taking one bit from each number and then ORing them together using an OR gate. The result is then fed to the output. In a real-world application, this may be used to merge bits together. And then the bitwise exclusive OR circuit takes two nibbles and then XORs them together. It does this with each individual bit from the nibbles by taking one bit from each number and then exclusive ORing them together using an XOR gate. The result is then fed to the output. In a real-world application, this may be used to flip only selected bits.
The fourth operation we want the ALU to do is addition. Here is a gate-level diagram of a single 1-bit full adder that can add two 1-bit binary numbers A and B, and also accounts for carry-in and carry-out values. In order to add two 4-bit binary numbers together, we will need a 4-bit adder, which can be implemented by stringing together four 1-bit adders. The easiest way to understand how a full adder works is by comparing it to how we do binary addition on paper. The sum outputs are like the digits we write below the line that are eventually put together to form the solution. The carry-ins and carry-outs are like the ones that we carry into the next column. For example, two zeros make a sum output of 0, and no digits are carried. 1 and 0 make a sum output of 1, but there is still no carryout. Two 1s will give us a sum of 0 and a carryout of 1. Finally, if there are three 1s in a column, the sum and carryout will both be 1.
The last piece of the puzzle in our ALU is our 4-to-1 mux. A mux, or multiplexer, is a lot simpler to understand than it may sound. When looking at the gate logic for a 2-to-1 mux, we see that it is composed of two AND gates, an OR gate, and one inverter. There are three input pins and one output pin. Feeding both AND gates is the select pin, which acts as a gatekeeper, allowing only the A or the B input to be passed on to an output. As with any truth table, by looking at the ones in the F column, we can see that we get an unsimplified equation of S0 A B 0 or S0 AB or SA B0 or SAB, which can be easily simplified to S0A or SB using Boolean algebra or K-maps. Under normal circumstances, we would ignore the zeros in the F column, but when dealing with multiplexers, the zeros are just as important as the ones. The simplified equation tells us that when S is equal to 0 or S0, we want the value of A whether or not it is a 0 or a 1. And when S is equal to 1, we similarly want the value of B. This can then be combined to make larger muxes that can handle more inputs, as we see in the finished 4-to-1 mux needed for our lab. The implementation of this lab had the potential to be very complex, as can be seen in this example here. Luckily, we were introduced to the ability to create our own subcircuit designs to aid in the simplifying our layouts. As can be seen here, by utilizing splitters and increasing the data bits on our input and output pins, we are able to create a layout that is easy to read, test, and troubleshoot. This simplification leads us to the principles of encapsulation.
One of the awesome takeaways from this lab is the fact that large or complex circuits can be built from smaller subcircuits. These smaller circuits each have a function by themselves, and then when combined, they are capable of completing more complex tasks. A 1-bit adder can be used to add two single bits together. When you combine four of these small circuits, you can then have a 4-bit adder. This can now do addition on a much larger number. You can then combine this with some bitwise operator circuits and a multiplexer, and you now have a circuit capable of performing not just addition, but a variety of function on a 4-bit number, and you also have the ability to select which function to use for the output. This idea of modularity and encapsulation is used in many different engineering and design fields, but it is a critical component when designing complex digital systems.
We hope you all enjoyed this lab as much as we did. The next time you hear the words cohesion, modularization, and encapsulation, remember that they are not just limited to computer programming, but are essential design tools in many different fields. We encourage you to use these principles in your future circuit design.